Hello again, this is the third video in the sequence of videos on equilibrium of rigid bodies, which is a topic in further mechanics, part of the further mathematics A-level CIE syllabus. And what you see in front of you is the question 11 either optional question from the paper from winter 2003 winter 2003 paper. Yeah. So this is the question I'm going to look at in this video. If you haven't yet watched the other videos about equilibrium of rigid bodies, I suggest you watch them first, and moreover I would suggest that you probably shouldn't be attempting this task unless you've already studied the topic generally. So if you like, you can. So if you do want to watch this video, you can read the question here, or at least read the first part of it. It's a bit difficult to put all of it on the screen. Can I manage that? No, not really. Well, yeah. So let's read together the description, and then let's look at each of the parts of the question in turn. A rectangular drawer, ABCD. So drawer here is a word for something you put your clothes in. If you're not a native speaker of English, as usual, my advice is don't worry too much about the exact meaning of words you're not sure about. Just look at the mathematical setup. So we have a rectangle ABCD. AD and DC are given lengths, and the drawer can move on a smooth horizontal surface. So that means that what the diagram we're looking from above. That is a plan view. So it means, of course, that the weight force will not be important. Okay, we have two handles at H and K. They can be pulled horizontally perpendicular to the front edge AB, so that would be the direction downwards on the screen. As you can see, the force P is pointing downwards. An attempt is made to open the drawer by pulling only on handle H. In this case, frictional forces F1 and F2 act at B and D from the sides of the drawer frame, impede, which means prevent opening. So maybe a detail which should have been made clearer in the question, although it's probably clear, but in case it isn't, B and D, you see those two shaded squares on the top left and bottom right corners, B and D. They are part of what's called the drawer frame, and they of course would be fixed. In fact, come to think of it, they really should in this question have stated explicitly, they should have stated that B and D cannot move. And that's important, of course, because if B and D can't move, then the motion of the rectangle, the drawer ABCD, can only be up and down on this diagram, or in real life it would be horizontally, forwards and backwards. Okay, so anyway, I hope the physical setup makes some kind of sense to you. You know, you've got your socks in the drawer and you want to open the drawer, but you're pulling using a force at position H only. You're not pulling at position K as well. Alright, so the normal reactions at B and D are N1 and N2 respectively. The first part of the question, if we assume the coefficient of friction at B is 0.8 and at D we have no friction or smooth, we have to show that the drawer cannot be opened by a force P applied to H. Now I'm going to shift over to my notes where I've copied the question already. Yeah, there it is. Assuming that the coefficient of friction at B is 0.8 and D is smooth, show the drawer cannot be opened. Okay, so let's attack this first part. Let me mark really clearly. There's D and there's B. These are the most important points on the diagram. These are the things, these are part of the frame, so they cannot move. And we're told that the contact at D is smooth. Well, that means that this friction force here, F2, will be 0 for this part. Meanwhile, the coefficient of friction at B is 0.8. So that will give us a maximum for the friction force F1 as a function of the contact force N1. Okay. Now, maybe the most important word in that whole question or sentence is this little word A. What is the significance of this word? It says A force P. Well, the significance is that we don't know what P is, and moreover we don't need to know. It's saying that whatever force P is, whether it's 10 newtons or 100 newtons or 1,000,000 newtons, the drawer will not open. Okay, now that might seem strange, so we should think about why physically that would be true. You know, usually if you pull something in this direction, it will move as long as the pulling force is strong enough. So what's going on here? Why would the drawer not move? Well, you probably can imagine from your physical intuition, in other words, your feeling of physically what would happen. Just use your imagination. If you try and pull, you know, you've got your socks in the drawer, you want to open the drawer, but you only use one hand and you only pull on one handle. Why doesn't the drawer open? Well, the obvious answer is that if you're pulling here to the left of the center of the drawer, you're going to create some kind of turning effect. And yeah, so in other words, if B and D were not there and the drawer were completely free to move, then the effect of pulling at point H would not just be to move the drawer forwards like this, but also to rotate it. Yeah, that's the big difference between further mechanics and M1, isn't it? That we appreciate that the position at which a force acts is important because it affects the moment or turning effect. So now we need to translate that into mathematics. How can we show that the drawer will not move because of this potential turning effect? Well, what I'll say first of all is the drawer cannot rotate because B and D are fixed. So B and D are fixed. As I said at the beginning, that is very important, and they should have emphasized it more in the question. Students often find this question difficult, and I think this is why. So because it cannot rotate, that we can say that we have rotational equilibrium. Excuse my handwriting, I seem to be out of practice with this pen here. So we have rotational equilibrium. That means we can do what? It means that we can take moments about a pivot, and as I discussed in the earlier videos, we can choose a pivot. It doesn't actually matter what the pivot is. We can choose any pivot, take moments, and we know the total moment, including clockwise and counterclockwise, will be 0. Okay, so now it becomes important to decide on a particular pivot point. Well, I've got a bunch of unknowns here. N1, N2, F1, F2 is 0, and P is also unknown. So I'd like to keep this equation as simple as possible. It is probably okay to choose almost any pivot, but I'm going to choose what looks like the most easy pivot, which would be B. So I'm going to choose B because both N1 and F1 will be excluded from the equation because they have 0 moment, whereas the forces N2 and P will have a non-zero moment about this pivot. So using the traditional notation, we write B with a curved arrow, meaning we're taking moments about B, and we can write the clockwise moment would be the force N2 times the perpendicular distance of the line of action of N2 from the pivot at B, which is 0.3 meters. And what would be the other side of the equation? Yep, that's right, we need the force P multiplied by its perpendicular distance from the pivot, which in this case is 0.8 minus 0.2 or 0.6. So we have a nice simple relationship there, that P is related to N2 by the fact that P is 1/2 of N2. Okay. Now remember, we need to somehow use the value of the coefficient of friction to deduce that whatever is the value of P, that we will not get the motion required or the motion desired, which is a motion in this direction. Okay, So what can we do? We've already taken moments. What other equations can we write down? Hopefully you're familiar by now that we can now take moments in the directions CD and AB. I'm going to write sorry, did I say take moments? We can resolve in the directions CD and AB. So resolving parallel to, let's say, CD, we get the simplest possible equation, because now we see that the contact forces N2 and N1 must be equal. Okay, well, substituting that in the previous equation, then I can note that P is equal to half of N1. So resultant force in the direction we want to see if motion is possible down the page. So that direction is CB. So resultant force in the direction CB is equal to P minus F1. So what will be the value of F1? Well, F1's maximum value, so if you write F1 equals mu times N1, then stop a minute. That's wrong. That's actually wrong in this problem. Can you see why that's wrong? Yeah, so that's wrong because F1 doesn't have to be equal to mu N1. That's limiting equilibrium, isn't it, or motion. In fact, the rule is that F1 is less than or equal. So it can be less than or equal to mu times N1, which is 4/5 of N1. So therefore, the law of friction, isn't it, is that the friction will take whatever value is required to maintain equilibrium, unless the value required to maintain equilibrium is more than the maximum value mu n, in which case the friction will take the maximum value. Yes, I know that's a very complicated sentence, but you should be very familiar with that concept already. So let's review this argument. So we deduced, in fact, that F1 will take the same value as P because it can. Yeah, because the maximum, might want to just add a little note here, because 4/5 N1 is bigger than half N1. So let's just quickly review that argument. First of all, we noted that rotation was impossible. Okay, so that means that we can write the equation of rotational equilibrium, which immediately tells us that whatever the value of P is, let's say I pull with 100 Newton force, well, N1 will be twice that force. So if I pull with a force 100, then N1 will be 200. And if N1 is 200, then F1 can be anything from 0 up to 4/5 of 200, which is, what, 160. And since P is pulling with a force 100, then F1 is allowed to take the value 100, because 100 is less than the maximum, which is 160. And however large I make my pulling force P, F1 will always be able to match it according to this model. Okay? So this is how it works in practice. I mean, it might be amusing to think about the practical reality, like what actually might happen if you pulled the handle very hard. If you pull the handle very hard, it's quite possible that the entire wardrobe, which consists of multiple drawers. You know, a wardrobe is usually like a large item of furniture. You know, it's a big box, isn't it? Again, this is for people who are not native speakers of English. If you're a native speaker of English, I don't think I need to explain what a wardrobe is, or a drawer. So I don't really mean a wardrobe, do I? I mean a cupboard. Like a cupboard has several drawers and handles, and you pull out the handle to open the drawer. If there are two handles, then, and you pull only on the left one, it might not open, it might get stuck, which is what this question is talking about. But if you pull really hard, I mean, you might pull the whole cupboard around like this. Yeah. But of course, we have a simplification here. This is a very simplified model, and the specific simplification is that B and D are fixed points. And if they really are fixed points, meaning that no amount of force will move them or break them, then it is true that it doesn't matter how big this force P is, we will never open the drawer. Okay, now I said all of that, I explained all that very quickly. So if you know, hopefully you've already tried the question, try to do it yourself so you can see what's going on. And hopefully you understood that argument. If you didn't understand that argument, maybe you need to just go back to the beginning, review it again, because there's not much point doing the rest of the question unless you properly understand that first part. Okay, so I'll continue now. Assuming you understood the first part, let's look at the second part. The second part, it says, we now assume, it's kind of a strange thing to write, but you sometimes see these strange things in questions. So assume now that f1 over n1 and f2 over n2 are always equal. And, as a separate point, don't forget that it is separate, that the coefficients of friction at B and D are both mu, but it doesn't specify what mu is. So we're going to have mu here and mu here. Again, let me highlight B and D. And we're going to have that the ratio of frictional force to normal contact force at B and D is the same. It doesn't mean it's equal to mu, but it's the same. Okay, don't forget the rule is f1 over n1 is less than or equal to mu. So we have, if you like, three quantities. These two ratios will always be equal at any moment according to that statement there. And both of them will be less than or equal to mu, and it's the same mu for both contacts. So those two are equal, and they're both less than or equal to mu. Hopefully that's clear. And then it says, part A, find the value that mu must exceed, which means find the minimum mu, if the drawer cannot be opened by a force applied, a P applied to H. So here we're just slightly changing the setup. First of all, notice F2 in this case is not 0, as it was in the previous part, because mu is not 0. But we're given this extra information that these ratios are the same. So let's again go through the equations that we can write down. As before, by the same token as before, we have rotational equilibrium because B and D are fixed, which means that the drawer cannot rotate. And as before, we can take moments about any reasonable pivot. I again am going to choose B because I don't really see a big deal about choosing you see, for example, if I chose H, I would have 1, 2, 3, 4 forces which are not 0. I would have 3 forces which would have non-zero moments. If I chose D, I would have again 3 forces with non-zero moments, and if I choose B, I have 3 forces with non-zero moments. So actually it probably makes almost no difference which pivot of those 3 I choose. If I chose some other random point, then the equation would be more complicated. So let's choose B again, although it's not a requirement. And let's write the equation of rotational equilibrium. What's the total clockwise moment? Well, we need to consider n2, multiply that by the distance 3. I'm going to assume that 0.1 meters is 1. Or in other words, I'm going to multiply my equation by 10. So I get n2 times 3 plus f2 times 8. And the anti-clockwise moment would come from the force P, which would be multiplied by 6. So let's call this equation 1. Now let's consider, let's consider the equilibrium in the direction CD. So again, resolving parallel to CD, again we get this very simple equation, n1 equals n2. And according to the question, if n1 is equal to n2, then it follows by looking down here that f1 is also equal to f2. So let's say f1 equals f2 equals f, and n1 equals n2 equals n to keep the equations a bit simpler. So let's keep going here. So we have something like what should I do here? Equation 1 becomes 3n plus what am I saying? 3n plus 8f equals 6p. Alright. Now, again, we need to consider under what conditions can we or can we not move downwards on that diagram. And we can, if we cannot move downwards on the diagram, which is the condition given in the question, if the drawer cannot be opened, so let's write that down. If drawer cannot be opened, then it follows that P is less than, perhaps, or equal to F1 plus F2. Technically, if we attain equality in that equation, then there will be no motion because zero net force is zero acceleration. But to be honest, that's not very important. So anyway, P is less than F1 and plus F2. And don't forget that F1 and F2 can take a maximum value. Sorry, maybe the simplest way to write it is like this, right? P is less than or equal to F1 max plus F2 max. In other words, yeah. So if they take their maximum value, P will still be less than that. So that gives us, now F1 we already said is equal to F2, so let's maybe write that as 2F max, but F max will be mu times n, won't it? So it will be less than or equal to 2 mu n. And so we have a condition, effectively we have a condition on mu in relation to P, but since we already have equation 1, we can substitute P into equation 1, creating an inequality which only has mu and n. Now, so therefore I will take this and substitute it into equation 1. Well, that's a very messy way of writing, isn't it? I want to try and use the most space I can, so I'll just move down a bit. So substitute this in 1 and we're getting 3n plus 8 mu n equals 6 times 2 mu n. So here I can sorry, I've actually slightly messed that up, haven't I? Sorry, just had to pause there because I realised that I'm presenting this in a very confused way. It's better if I don't write that, I think. If we just say that P is less than 2F max, because we're talking about the limiting case if we're finding the lowest possible value of mu. So therefore, instead of writing it like that, we could say if P is less than 2F max, and here this F would also be F max in the limiting case, so we'd be writing something like 3n plus 8F max. Now, because P is less than, so let's divide that by 6, and that's our equation for P, and that P is less than or equal to 2F max. And we can see from this that we've derived a relationship between the maximum friction and the contact force. So therefore 12 minus 8 gives me 4, doesn't it? So 3n is less than or equal to 4F max. So therefore F max over n is less than or equal to 0.75. So mu is sorry, that's the other way around, isn't it? F max That should be bigger than. F max over n is bigger than or equal to 0.75, so mu is also bigger than or equal to 0.75 because mu is F max over n. So let me just review that again because I got a bit confused in the middle there. First we had equation 1, which was simply rotational equilibrium. Then we recognised that n1 is equal to n2 and f1 is equal to f2. So we've just really got two quantities, f and n. And then we say if the drawer cannot be opened, it means that we cannot get a positive net force downwards on this diagram, which means that P must be less than or equal to F1 plus F2. So that means P will be less than the maximum possible values of the friction. That means that and then we substitute that in equation 1 and we get a relationship between the maximum friction and the contact force, which itself gives us a minimum value for the coefficient of friction mu. Okay, hope that's pretty clear. Now we have one last part of the question, and it's important to note that if I go back to the original question, part B is still under the condition that f1 over n1 equals f2 over n2, and the coefficient of frictions are mu in both cases as before. But now, slightly more complicated question at the end here. Now an attempt is made to open the drawer by applying at H, in addition to the force P, a horizontal force Q along the front edge. Let me emphasize the direction along the front edge means AB. AB is the front edge. They probably should have written that. The reactions of the side of the drawer frame are still B and D, no change there. But now we are given the value of mu, 0.8, and we're also given that the drawer is on the point of moving. This is one of those code phrases that means limiting equilibrium, which you should be familiar with those kind of code phrases from doing Mechanics 1 in A level. So we've got limiting equilibrium, we've got the value of mu, and what we're asked to find is two specific things, which is underlined in red, the direction of the force Q and the ratio of Q to P. So they told us that Q acts along the front edge, but they didn't tell us the direction being to the left or to the right. So if I draw Q acting to the left, we can guess the direction of Q. I mean to the left or right, and then we can verify, which means that if our equations show that Q is negative, it means that Q is to the right. I hope that's clear. That's a useful trick to remember, that when if you have a slightly complicated problem where you're not 100% sure of the direction of a force being well, you're sure of the line of action of the force, but you're not sure of its direction, you can simply work out if it's positive or negative. Okay, so there's a slight difference here. We do have mu. Mu is given. So mu is given as 0.8 in both contacts, and also limiting equilibrium means that F1 equals mu n1 and F2 equals mu n2. That's just given as a fact. Okay. However, we cannot make the assumption, or we cannot deduce, that F1 equals F2 or n1 equals n2, because the situation is slightly different here. And the reason it's different is because the force Q acts along the same line as n1. Nevertheless, it's just a matter of algebra here, isn't it? As before, let's go through the equations that we have available. To summarize, in any complicated problem of this type, a two-dimensional problem of equilibrium, we have basically three equations available, which means we basically have three unknown variables that we can find. Before we do the algebra, let's investigate this as a system in those terms. So let's say 1, 2, 3 equations. What are those 1, 2, 3? First one is moments, and you can choose the pivot, such as B, or you could choose H or D or some other pivot. But there's little point in trying to do more than one moments equation because it will basically give you the same information. It's worth thinking about that. And it's a useful practical tip, even if you don't think about it, which is that you rarely have, theoretically never get any value from writing a second moment equation. It's usually just a case of choosing whichever one is most convenient. Here it doesn't matter very much. B or D is fine. Then we have resolving equations in any two perpendicular directions. So you could say parallel to and perpendicular to some particular direction. Again, theoretically, you could choose any two non-parallel directions. That would give you the required information. I mean, you could resolve, in some random direction L, and then resolve in some other random direction Q, which are not parallel. Simply the fact that they're not parallel will ensure that you get the full information from resolving, but it's incredibly rare that you will want to do it like that. You'll basically always want to do it in two perpendicular directions. So these three equations are what we're going to write down, and forgive me for spending so long on this, but I'm just trying to show you some general principles which will apply in any situation. And by doing that, we will be able to identify the value of three unknown variables. Now, what are the unknowns here? F1, F2, N1, N2, then we've got P, and we've got Q. Mu is not an unknown, mu is given. So we seem to have 6 unknowns, but do we really have 6 unknowns? Well, no, because we already have these two equations, which mean that, let's say, F1 and F2 are already known in terms of N1 and N2, and P and Q are different unknowns, but the question is asking for the ratio of Q to P, so we actually only need the ratio P over Q. So that's 1, 2, 3 unknowns. So from this I can deduce that this system is soluble, it can be solved, and it's just a question of doing it. Okay, so 3 equations. Let's start with moments. As before, I'll take pivot B, but it doesn't really matter. So pivot B, I'll write them down here. Number 1, moments about B. Okay, B is a good choice because Q will not be included in this equation. I'll just get 8F2, again multiply the equation by 10. I don't want to use decimal places. So yeah, 8 times F2 plus 3 times N, sorry, I better leave the diagram visible, plus 3 times N2, those are the clockwise moments, is equal to 6 times P. So that's the rotational equilibrium equation. Now we can write down the resolving equations. First of all, parallel to AB, I have N1 plus Q equals N2. So now N1 and N2 are not equal because of that force Q. And the third equation, I can write equilibrium in the direction AD because we have limiting equilibrium, which means we have equilibrium, which means that P is actually equal to F1 plus F2. So now I want to combine these equations. The simplest way to do it would be first to write a relationship between well, let's substitute equation 3 into equation 1 and use F equals mu n. And so by doing that, I'm going to make all these terms F2, N2 and P, they're all going to be expressed in terms of N1 and N2. So I'll get 8 times F2, which is mu N2, which is 4/5 being 0.8, times N2 plus 3 times n2 equals 6 times p. P is f1 plus f2, which is mu times n1, which is 4/5 of n1, plus mu times n2, which is 4/5 of n2. So you see here I can rearrange this equation to show the relationship between n2 and n1. Let's multiply it by 5, so we get rid of these 5s in the denominators. We'll get 32 plus 15 times n2. Sorry, that's not all of it, is it? 32 plus 3 times 5n2. But then let's subtract from the other side of the equation 24 times n2, and on the right hand side of the equation I have 24 times n1. This simplifies to 23, so n2 is 24 over 23 n1, and that means that q is positive, because look, if we look at equation 2, n1 plus q equals n2, well, if n2 is 24 over 23 n1, then it's bigger than n1, so n2 minus n1 is positive, so q is greater than 0, so q goes to the left on the diagram. So because I drew q pointing to the left, if its value is greater than 0, it must be pointing towards A, towards the left side of the diagram. And then finally we need to find the value of p over q, so to do that I'll just simply write, actually q over p, yeah. So q over p, I'll just simply write it directly from the given equations. Q from equation 2 was equal to n2 minus n1, and p was f1 plus f2, so that's mu n1 plus mu n2. Well, mu is 4/5, so that gives me 5 over 4, taking out the factor mu. n2 minus n1 would be 24 over 23 n1 minus 1 n1, and in the bottom I'm going to get n1 plus n2, which is 24 over 23 plus 1 times n1. So that's 5 over 4, cancelling n1, and we get 1 over 23, and on the bottom we get 24 plus 23, which is 47 over 23. 23's cancel, so I get 5 over 188, which is the value of the ratio of q to p. Okay, so that last stage I went through it quite quickly. It's just calculations, but you know that kind of set of 3 equations is extremely common. I've found in the exam is that they want you to be able to combine resolving and moments equations to solve a system of 3 unknowns. Sometimes it's more than 3, like here arguably there's 6 unknowns, but you need to recognize that some of them are connected. I mean, you could argue there's actually 5 equations and 6 unknowns, and that's why, because these 2 here are 2 equations. Okay, so hopefully that was fairly clear. It is a difficult question, so if you tried it yourself and you got stuck, don't be too unhappy about that, because I can't remember any other question than this one that has challenged students as much as this one. And maybe there's 1 or 2 others that have been very difficult as well. But you know, this is the kind of skill you need to practice. So hopefully that was useful, and I will stop there and see you again sometime soon.